Hello everyone! Today we are going to talk about electrobioconversion of carbon dioxide to bioplastic. Let me introduce my teammates first.
Hi, I'm Jean Brownell.
Hi, I'm Olivia Eddings.
And my name is Wentao Dai. So, why do we want to convert carbon dioxide to bioplastic? The story starts from 1800s. Since the dawn of the Industrial Revolution, atmospheric carbon dioxide concentration has been steadily increasing, driving climate change with alarming consequences. As a global community, we are witnessing more extreme weather events, rising sea levels, and widespread crop failures. All of these devastating impacts remind us that urgent actions are necessary to reduce carbon dioxide emissions and protect our fragile ecosystems.
Several environmental issues stem from plastic production. The production process itself releases harmful gases such as carbon dioxide and methane into the environment. This production process begins when raw materials are extracted and derived from natural gas and crude oil. These methods can disturb ecosystems, water flow, and cause damage to any surrounding soil and land. Ethylene from crude oil and propylene from natural gas are the primary sources of plastic production because they provide cheap alternatives to plastics that are derived from plants. These materials are then processed in refinery plants to obtain and break down compounds that are needed for plastic production. But doing so can release toxic substances into the air and soil. These chemical compounds are then modified to produce what is known as resin that is molded into plastic nurdles for manufacturers to melt down and then create plastic products. However, this process can discharge toxic substances into the air and cause microplastics to escape into waterways. In 2020, the production of plastics generated around 0.8 billion tons of greenhouse gases. By 2050, it's expected that number be around 2.3 billion metric tons, just from the annual emissions from resin and fiber production. Any remaining annual emissions might come from the incinerations of plastic at the end of its life cycle. A life cycle analysis indicated that the best end-of-life treatment for plastic was landfilling, compared to incineration or recycling. However, the leaching of plastics during the time that it's supposed to degrade from the landfill is a major concern.
Plastic waste is a large issue. Plastic does not readily decompose, and only 10% of plastic in the world is recycled. The plastic degradation that we do see is a physical degradation that's primarily driven by sunlight and impact on the plastic pieces. So plastic just breaks down into smaller and smaller pieces, the smallest pieces being called microplastics. The decomposition rate for this plastic is on the time scale of 10 to 1,000 micrometers per year. This lack of plastic degradation has severe environmental impacts. Every year, over 8 million tons of plastic are entering the oceans, and microplastics have been found in nearly all waterways, and recently, studies have shown that they're also found in human bloodstreams. This high accumulation of microplastics in humans can have an impact on the immune system and our metabolism. These microplastics are also neurotoxins, reproductive toxins, and carcinogens, posing severe human health risks and environmental health risks. Bioplastics, on the other hand, are a much more environmentally friendly product. Bioplastics are plastics that are made either fully or in part by renewable resources. Because of this, bioplastics are often biodegradable or compostable, and they're broken down by microorganisms into CO2, water, biomass, and inorganic compounds, and they can be fully broken down, as seen by the picture on the right-hand side of the slide. This happens on a rapid timescale on the order of days to months. Studies suggest that converting all of our plastic production to bioplastics would reduce greenhouse gas emissions by 25%. Also, these natural degradation methods, as described, do not produce toxins that are introduced into the environment in the way that plastics do. Also, there's no net increase in CO2 as they decompose because the CO2 that they release as they decompose is the CO2 that they were formed with, so it's a net zero on CO2 production.
Here, I will introduce a technology that converts carbon dioxide into organic chemicals that address those problems we just discussed. This figure demonstrate the underlying mechanisms of using renewable energy such as wind turbines and solar panels to convert carbon dioxide into organic chemicals, whether it is biofuel for energy storage purpose or bioplastic as a more valuable product. The reactor consists of two electrodes, an anode and cathode. These electrodes are connected by a power source that provides voltage to drive electron flow. On the anode side, water molecules lose their electrons and are oxidized to form oxygens and protons. Meanwhile, at the cathode, organic chemicals are produced catalyzed by microorganisms. This interdisciplinary project combines the field of chemistry, biology, and engineering to create a novel carbon dioxide to bioplastic conversion process. The research in this field aimed to overcome the challenges faced in traditional plastic production method discussed by Olivia, and to demonstrate the potential of this cutting-edge technology in reducing carbon dioxide emissions, while also addressing the environmental impact of conventional plastics. Next, I will delve into details of this conversion system and outline the metabolic pathway inside microbes, as well as how microbes have been engineered to utilize electrons and carbon dioxide to produce bioplastics. In this section, I'm going to discuss the microbial design of the electromicrobial conversion with C2, as known as EMC2 system, to efficiently produce value-added products from carbon dioxide, especially biodegradable plastics called polyhydroxyalkanoate, as known as PHA. The EMC2 system demonstrates an innovative solution for a sustainable economy, addressing challenges like carbon emissions and plastic pollution. This research focused on medium-chain length PHA, which are less brittle than their short-chain counterparts, making them more suitable for replacing petrochemical plastics. To improve PHA production, they tackled the metabolic barriers for lower productivity using a synthetic pathway design. They considered four aspects: ethanol and acetate conversion to acetyl-CoA, PHA de novo synthesis, PHA synthesis from fatty acid beta oxidation products, and prevention of PHA degradation. By implementing a four-module design, they successfully enhanced the conversion of C2 products to PHA. These efforts including knocking out the PHA Z gene to minimize degradation, overexpressing PHA-G, PHA-J4, and PHA-C1 to improve acetyl-CoA conversion to PHA precursor. Their work shows the potential of the EMC2 system in producing biodegradable plastic from carbon dioxide, and paving the way for significant environmental impact reduction.
This electromicrobial conversion with C2, also known as EMC2, is a game-changing use of CO2 as a feedstock to produce a variety of chemicals and products. The first one being that the two carbon intermediates have much higher reducing equivalent and more rapid mass transfer, thus improving productivity as compared to their one carbon, hydrogen, and electron-based pathways. Also, EMC2 relies on high flux primary metabolic pathways, which gives it a biochemical advantage. Additionally, acetate and ethanol are the preferred substrates, and with their lower toxicity, they allow for higher cell biomass, adaptability, and yield. Acetate and ethanol also are converted to acetyl-CoA, which benefits the TCA cycle and increases the PHA bioproduction rates. Additionally, all carbon that's used for cell growth and bioproduction is generated from CO2. It also does not rely on any organic substrates. The overall process described previously has demonstrated a viable and high-yield pathway for CO2 to PHA production using the EMC2 system. This leads to far-reaching environmental impacts for both carbon emission reduction and plastic pollution mitigation. The soluble C2 intermediates have many benefits, including facilitating rapid mass transfer, readily entering primary metabolism, having less toxicity, carrying more energy and electrons, and serving as better molecular building blocks for many microorganisms. Additionally, they achieve 6 times the microbial biomass productivity compared to C1 intermediates and 8 times compared to hydrogen-driven routes. The medium chain PHA polymer products also have benefits, including favorable biodegradability and mechanical properties. Also, they're less brittle plastic products than the short chain ones, such as PHB. Additionally, PHA production via this method is a 6.4 times higher rate than the highest reported photosynthetic PHA production. Also, by producing biodegradable plastics from CO2, we allow for our carbon footprint to be reduced and mitigate the global plastic pollution.
Let's look at the challenges of this process. Pseudomonas petitus has been engineered to be utilized in various substrates to produce a variety of commercial products. Even though it can tolerate harsh environmental factors, the wild strain does not grow well in the whole medium containing reduced carbon sources. To overcome this barrier, Pseudomonas petitus needed to be grown for multiple generations. One challenge associated with this process was the adaptive evolution to achieve continuous carbon fixation and biomass accumulation. A second challenge is the fact that the bioconversion of substrates to PHA has less energy conversion efficiency than shorter chain length products like PHB, as the hydrocarbon side chain of PHA is more reduced and thus requires more energy and reductants to produce. However, this longer hydrocarbon side chain of PHA improves the mechanical properties of the bioplastics and makes it more applicable for a broader placement of petrochemical plastics, as this process could be slow and costly. Another challenge is substrate availability. Limited supply of substrates, even nutrient supply, can hinder large-scale production, further raising the concern of how this process could be scaled to broadly replace everyday plastics. Another challenge is the high cost associated with upstream and downstream processing that comes with purification and recovery processes that could ultimately affect the economic viability of this PHA production. Finally, PHA needs to be cost competitive and meet similar performance standards as conventional plastics. This is a challenge because conventional plastics are already much cheaper to produce and are known to be very durable. Despite all these challenges, this process is a viable route to reducing carbon emissions and plastic pollution.
Our Earth is facing an unprecedented challenge, and it is our collective responsibility to take action and protect our planet for generations to come.
As the global temperature rises and the consequences of climate change become increasingly evident, the need for innovative solutions in carbon dioxide capture and utilization has never been more urgent. The world needs passionate minds, like all of you here today, to join forces and help develop groundbreaking technologies to mitigate the catastrophic effects of greenhouse gas emissions.
In the field of engineering, we possess the unique ability to apply our technical knowledge and creativity to address this critical issue. Whether it is through designing cutting-edge carbon capture systems, improving the efficiency of renewable energy sources, or devising sustainable processes for converting waste carbon dioxide into valuable products, we, as engineers, have the power to make a tangible difference.
I urge you all to consider dedicating your research efforts to the realm of climate change and carbon dioxide capture. Not only does this provide an opportunity to develop your skills and contribute to the global scientific community, but it also allows you to play a vital role in protecting our planet.
Together, let us harness our collective intelligence and determination to create a more sustainable and prosperous future. The time to act is now, and the world needs our commitment, creativity, and expertise. Join me in this mission, and let's make a difference for our Earth and all its inhabitants.
With that, we would like to end our story today. Thank you so much for watching. Looking forward to see you all next time.